Please join again. I do not know. No, I haven't started sharing anything. I will do it. I'm just giving a sort of explaining a little bit where we are going. Then I'll start sharing. If some people have got left out because of recording or whatever, please join again. Yeah. So okay. What I was telling is, if J is positive, it will force the spins to align parallel to each other. Then it gives you a ferromagnetism. That is what we discussed last time. So that means, so far we discussed 3 different magnetic orders. In a nutshell, I'll tell. The first one is diamagnetism, where all the electrons are completely paired. Thereby, the total angular momentum, orbital, as well as the spin angular momentum are is 0, so that there is no net angular momentum. And I showed you that through experiments as well as theory, there is an intermediate relation between angular momentum and the magnetic moment. So if you do not have any net angular momentum, then there is no magnetic moment. So the magnetic moment only comes through induced effects in the diamagnetic materials. In the paramagnetic materials, there is a permanent magnetic moment because of unpaired electron, but these electrons are not coupled to each other. So in the absence of field, the average is 0, and in the presence of field, they start aligning along the field direction, thereby giving rise to some magnetization, which is positive. Susceptibility is positive. That means they try to orient along the field. Okay, and with increase in the field, this magnetization increases. It's linear. So the requirement is you need to have unpaired electron and non-interacting. So there should not be any coupling or interaction. Then the third order that we have seen is ferromagnetism, wherein we said, okay, there is an interaction, which we did not go into details, but I said there is an interaction which basically couples these moments, neighboring moments at least, along a particular direction, either parallel or anti-parallel, depending on the sign of J. So that is all we discussed so far. So then I'll continue I'm going to share now the PowerPoint from that point onwards.
Sir,
then yeah.
Sir, this spin which you are talking about, the exchange interaction, that Si dot Sj, these spins are in the same energy level or in different atoms you are talking? Because in the same energy level, the spins have to be means one has to be anti-parallel to the other, right? In the same level, it has to follow that exclusion principle. So this spin, what is it?
Yeah, see, these are spins sitting in the neighboring atoms. Okay, neighboring atoms, they will align parallel. If the atoms themselves are so close by, then what happens is it will prevent them for orienting parallel, and they have to antiferromagnetically coupled. Okay.
Okay.
Yeah.
Okay.
That's why I think the same question was asked in the class also, Google class. I tried to explain. Yeah.
Sir, here that exchange interaction, there should be a summation, right? Minus 2Jij.
Sigma over I comma j. Actually, I'll give you a total expression. Now, let us assume we are only looking at a 2-electron system. Okay, we are looking at a 2-electron system. I am only talking about these 2 electrons. I mean, it's like a 2-body problem, but I have to sum over the entire solid, because this is seen in the materials in a solid. So I have to, of course, sum over all the atoms. Okay, but I'm saying either they are coupled or no coupling, or if they are coupled, if they are so close, J is positive, then they couple parallelly. So that is what I'm saying, but we will go there. Okay.
Okay, sir. Sir, I have more questions from last class. I'll ask at the end of the class.
Yeah, wonderful. Okay. I mean, if you, because I'm not really going to discuss too much of ferromagnetism now. I'll move on. As I told you, I'll move on to antiferromagnetism. But I encourage you to read the notes which I uploaded on the exchange interaction.
Yes,
Can you please go through that notes? And also, if you have questions, you can either write to me or call me or whatever, like we can discuss at the end of the class also, right? Yeah. So I'll now start presenting. First, I have to start present screen. Present now. Entire screen. Okay. Do you see now? Am I?
Yes, sir.
Can you see? So the last point which we were discussing in the ferromagnetism before we close the class on that day is that in magnetism, we have to be more specific. Which magnetization are we talking about? Okay, so I wanted you to get a clarity on that. So I'm just explaining here. So magnetization is always measured in the presence of field in general. Okay, we will measure magnetization by applying the field, and it can be measured at any temperature. Okay, starting from like lowest temperature ground state. Let us say T is equal to 0 theoretically. Okay, but from the lowest temperature to the highest temperature. So when we say magnetization, that is in-field magnetization or measured magnetization, that means it is measured at T is not equal to 0 in general, because T is equal to 0 we cannot approach to start with, and H is not equal to 0. So that means there is some field which is present, and then you are measuring the component of the net spin, as someone was pointing out. You have to sum over all that, in the net spin along the field direction is the measured magnetization. And this magnetization will have a maximum value, which is nothing but the saturation magnetization, when all the spins are oriented along the same direction. That means further increase in the field cannot change anything. Okay, so this is the maximum value that the system or material can have. So that's called saturation magnetization. So it can be, it is possible, like except in dia and other materials, it is possible to get this, except that depending on, suppose if you are looking at a paramagnetic material, you need to apply a very large field, because the thermal energy, you are working against the thermal energy. So the field that is required to saturate will be very large. But on the other hand, if you decrease the temperature, because you are decreasing the thermal energy, the field that is required to saturate the magnetization will also be small. But nevertheless, the value itself, so-called saturation magnetization, will not depend on temperature. This point is very, very important. You please understand. What I am trying to say is, because system will saturate when all the movements are oriented along a particular direction. Do you understand? For that, depending on the temperature, either I have to increase the field or small field itself is sufficient. But I will not call it as a saturation unless this component is maximum. So this component value itself will not depend on the temperature. So it is independent of temperature. At any temperature, it will have the same value. Only thing is the field that is required will be different. Is that point understood?
So then this saturation magnetization basically is independent of temperature.
Yes. But the field that is required is temperature dependent. Please listen, because these are two competing factors. So if I am doing it as I'm magnetizing the specimen at a lower temperature, then the field that is required to saturate will be smaller. But if I increase the temperature, then correspondingly the field will also increase, because it is working against the thermal energy. Is that point clear?
Yes, sir. Yes.
Yeah. You need to think. Okay, little bit. I will try to go slow, because the other day you complained that, someone felt that I'm going fast, so I'll try to go slow, and I'll also ask feedback at every point. Please respond. One of you have to volunteer, or if you have a question, stop me. Okay. So then in ferromagnetic materials, I am introducing another magnetization, which actually last time also we discussed. This is spontaneous magnetization. What it means is, this material by intrinsically has a net magnetization. You understand? Of course, within a domain. Okay, what are domains and all will come. Why domains are there will come later. But now you say that you have a domain. That means this domain is the region in which the spins are all coupled and oriented along a particular direction. So that region, the space or the spatial extent over which the spins are all coupled and oriented along a particular direction, now I am calling this as a domain. So within the domain, there is a net magnetization. And this magnetization is present in the absence of the field. I don't need to apply any field. From where it is coming? It is coming because of the interaction between the spins. So the spins are making them to polarize along each other, so that they have a net magnetization. So I give here an example of your student unions. Okay, so there are different unions in your body, like ABVP, SFI, and all that. What I am saying is, this domain is like one of those unions where no individuals will have some agenda, some philosophy, some idea, which is coming not because of any teacher. It is coming because of the interaction between each other. A new student joins, then he will be influenced by this group, and then he will orient along that direction. So similarly, these spins within the region are there because of this interaction. Okay. So whereas the paramagnet is like, before you join this place, you are all independent. You are not interacting. So if it is so then you react in individual way. But once you join and get associated, then you react collectively. So this is a collective behavior, which is, I'm calling it as spontaneous magnetization. But this is not the only domain. Okay, there are other domains in the system. Why other domains will come? Why they are orienting in different directions? Today we'll discuss. So because of that, the net magnetization, that means over the sample, can be finite or can be zero. You understand? So that we will see. What I am talking about here now, spontaneous magnetization is magnetization within a domain which is present up to t is equal to Tc. This fellow is finite up to Tc. Beyond Tc, this domain itself is not there because there is no interaction, there is no collective behavior. So the spins are all random. So spontaneous magnetization is zero. But this doesn't require any field. So that's why what I put is spontaneous magnetization is a function of temperature. Okay, I should have actually put T less than or equal to Tc there also. It will be there up to Tc. And H is not equal to zero. You don't need to apply any field to it. But can I measure? Experimentally, I cannot measure unless I apply a field. So if I measure, what do I get? I get actually the measured magnetization, not this. So this will be derived from this measured magnetization. And if you plot this as a function of temperature at a field, you will see this kind of a behavior. So what you will have is, at the lowest temperature, so as to say, it will have a maximum magnetization, and in fact at T is equal to zero, for a ferromagnetic body, the spontaneous magnetization and the saturation magnetization both are one and the same, because at that temperature there is no thermal energy, there is no decrease in the net orientation. All the spins are oriented along a particular direction. The sample is also saturated. So at that temperature, this magnetization will have a maximum value at T is equal to zero. But as I increase temperature, because of the thermal energy and this spontaneous magnetization keeps on decreasing, because now those pins are trying to hold together, thermal energy is trying to randomize it. So there is a competition between these two. And at Tc, this coupling, this interaction energy will no longer be able to hold the spin set together, and it becomes completely paramagnetic at that point. So that's why there is a phase transition from ferromagnetism to paramagnetism. And the signature is that the spontaneous magnetization goes to zero at that temperature. So that is also another way. That is order parameter. I was also talking about order parameter. So order parameter is also a measure of how much of order the system has. In this case, spin order. Okay, there can be different depending on the phase transition. We will talk about different orders. In this case, it's a spin order. So the spin order is maximum. The spin order is maximum. That means order is maximum at T is equal to zero. And the order parameter is, this point is plus or minus 1. That I will explain, because it can be either along any direction or opposite to that, because this is a dot product and it's a scalar. So there is no specific direction. So depending on where I'm measuring, either it can be along that direction or opposite to that. So this is maximum. This value goes on decreasing and it will become zero at T is equal to Tc. So that's what I am talking about here, that at T is equal to zero, spontaneous magnetization is also equal to the saturation magnetization. So I have introduced you to three different types of magnetizations itself. Okay. Any question on this slide?
Yes, sir.
Yeah.
Sir, that measured magnetization which we see experimentally, so that is actually equal to M saturation plus M spontaneous?
No. Measured magnetization depends on for a given system, depends on many factors. It depends on the temperature where you are measuring, field that you have applied also. For example, given a ferromagnetic body, even below Tc, if you have applied a small field, let us say, okay, then you may not be measuring the entire component of magnetization. So it will not be equal to the saturation or spontaneous also, because in a material, if you look at it, there are different domains. Okay, so we are not measuring the measurement magnetization within a domain. We are measuring the entire sample. So unless all the domains are oriented along a particular direction, we will not get the entire total saturation magnetization. That will happen only if the field is strong enough. You understand? So measured magnetization depends on these two factors. What is the temperature? What is the field that you have applied to measure? Okay.
Okay,
so that is why what I'm saying is, here if you look at carefully this notation I am using, M depends on T as well as H, and both have to be not equal to 0. That is a kind of a thing. So if you say what happens to T is equal to 0, T is equal to 0, of course it's the maximum magnetization. That is nothing but saturation magnetization. Okay. And if it is a ferromagnetic body, that is also equal to spontaneous magnetization. On the other hand, saturation magnetization, the field has to be greater than H saturation. Okay, here actually I will put the other one also, that here T should be less than or equal to Tc. Okay, since I have put here H is greater than or equal to H saturation, here T should be less than or equal to Tc. Only then I can talk about spontaneous magnetization. Okay, any other question?
Yes, sir. Sir, leading to an external magnetizing field H, there's external magnetic field intensity H, there's a measured magnetization which we have, and then we'll have the magnetic field inside, the total magnetic field inside.
Yes, wonderful. Actually, B is equal to H plus 4 pi m. With the first day when I was talking about units, I am talking about, okay. B is the magnetic induction in the material, which is equal to the applied field plus magnetization with the units proper. Okay.
Sir, my question is, as you have said that T lesser than equal to Tc, when H is 0, means when magnetic field is, external magnetizing field is not applied, so still there will be a spontaneous magnetization existing, right?
Yes, correct.
So that spontaneous magnetization, will it lead to a magnetic field itself?
Yes, it will also lead. That is why, so actually, see, in the Weiss molecular field theory, I am sure you must have got exposed in BSc at some point. What my Weiss molecular field is, why there is a coupling between the spins. Normally, if you look at a paramagnetic material, the spins they don't talk to each other. They talk with respect to the field. So the orientation is decided by the field. So if you extend the same argument to ferromagnetic material also, why these spins are getting oriented along a particular direction? There should be some field. Yes, there is a field. But I am saying that there is no external field. Yes, there is no external field. Then this field that I am talking about is an internal field or Weiss molecular field, which is coming because of the coupling between the spins. So it is like, I told you the other day also, it's like chicken and egg. So which one is responsible for what? So the internal field is responsible for the coupling, and coupling is in turn responsible for the internal field. And if you see, the internal field is actually proportional to the magnetization at any given temperature, with a proportionality constant called Weiss molecular field constant. And if this magnetization itself is 0, it will be 0 for T greater than or equal to Tc. So if it goes to 0, the internal field will be 0. So there is no coupling. But for temperatures less than Tc, because of the coupling, there is an internal field. Okay.
Sir, is that internal field, is it not that strong enough? So if we have an iron bar, it does not attract, right?
It is very, very strong. Actually, you have to wait for some more time to answer for my answer. In fact, it is very, very strong, and it is much stronger than the applied field that you apply externally. Your applied field is only a small fraction of the internal field. But then what happens is you do not have a single domain. If it is a single domain, it would have attracted. But because of various reasons, which I will discuss, okay, you have to wait either today or tomorrow's class. It will become, in next week's class, it will become clear.
Sure.
Why it will split into domains. Why there is an iron nail which you find on the road, even though it is supposed to be magnetic, ferromagnetic, and it should attract, it will not attract. So these questions I will answer.
Okay, sir. Okay, sir.
You understand? Okay. Okay.
Okay, sir.
Fine. So you have to wait. So then I will proceed to next order. Okay. This order is called antiferromagnetism. I'll not spend too much details on this, because for our experiments we will consider ferromagnetic and ferrimagnetic for that reason. But to introduce ferrimagnetic, I need to discuss about antiferro. So with that notion I am explaining here. So I will go back to my Hamiltonian again, the exchange interaction Hamiltonian. If you people remember, I will keep using this. That is nothing but minus 2Jij Si dot Sj. So in that, I told you that if Jij is negative for whatever reason, okay, if the coupling between the radial coupling of these wave functions are anti-symmetric, so Jij is negative. So the energy can be minimized if only Si and Sj are coupled anti-parallel. That means if that cos 180, the angle between them is pi. If cos 180 is -1, so there is already one minus sign and J is minus. So the three minus signs will give you minus 2J square, which is again negative energy, which is a stabilization, which basically stabilizes the system, minimum energy configuration. So in those configurations, the spin system will prefer to couple anti-parallel to each other. That is what I am trying to show here. So this is also a cooperative. That means there is a coupling between the spins. Of course, you need to have an unparalleled, unpaired electron to give rise to a net spin magnetic moment. So you need to have unpaired electron, and this is cooperative, long range. But point is, the requirement is J is negative. So J is negative because of that they coupled anti-parallel. And similar to your ferromagnetic to paramagnetic transition, here you have antiferromagnetic to paramagnetic. So high temperature phase is always paramagnetic. So this coupling, that means again here I bring the same notion that this coupling energy competes with the thermal energy. So if the coupling wins over, then I will have an antiferromagnetic order, and if the thermal energy wins over, then I will have a paramagnetic. And the temperature at which this transition takes place now is called Néel temperature. Unlike a Curie temperature, in the ferromagnets we call this as a Curie temperature and denoted by Tc, where we call this as Tn and denoted by Néel temperature. Okay, this is again ordered state to a disordered state. This is also a phase transition from an ordered spin. This is also one kind of order. It's not like completely parallel, but it's an anti-parallel order nevertheless. So this is another thing that you need to know here is that these spins, the magnitude themselves are equal. So in this case, as well as in the ferromagnetism case, the magnitude of the spin at a given site is same. Either they are coupled parallel or anti-parallel. In this case, anti-parallel. So if you say the magnitude is same and coupled anti-parallel, so the net magnetization is 0 again. So there is no spontaneous magnetization in this case again. So because they are all coupled completely anti-parallel to each other, so the net magnetization is 0. So how do people understand? People actually do very clever tricks. What they do is they will consider this antiferromagnetic material here, as you can see. Okay, so this is a lattice. At each lattice site, there is an atom, and there is an unpaired electron associated with that atom, let us say. So as I demand that it has to have an anti-parallel configuration, neighboring spins. So if my yellows are pointing up, let us say, my pink, magenta is pointing anti-parallel to each other. So you see that this is an anti-parallel configuration, this is an anti-parallel configuration, so is like this, right, at this case. So this is anti-parallel configuration. So this can be decoupled into two sublattices which are ferromagnetically coupled. So this is a little involved, please listen. What I want is I have this kind of antiferromagnetic structure that can be decomposed into two ferromagnetic sublattices. But what I am looking now, this lattice, if you see, this atomic unit, you see, I am talking this yellow and this yellow, ignoring this yellow. So this is actually separated out, and I am considering that all the spins are ferromagnetically coupled. So why am I doing? Because I already know how to deal with a ferromagnet, so it becomes easy. And then I'm saying, okay, there is another ferromagnet. This is also ferromagnet because all the spins are parallel to each other. But these two ferromagnets are coupled antiferromagnets. So then the problem becomes simple for me. So I have, you can say the net magnetization because of this sublattice, the net magnetization because of this sublattice, both are equal and opposite. So the net magnetization is 0. So there is no spontaneous magnetization. Okay, I'll wait here for your questions. So 2 minutes.
Sir, how is this assumption correct?
Is correct
that we have.
Yeah, It is
we have broken it into two parts, but there will be interaction, right? If we keep it as one.
Yes. Actually, you can first order, you can take this. Second order is, okay, I'm not ignoring the interaction. I'm bringing the interaction in terms of, again, the net magnetization because of that, net magnetization because of these are interacting. So, of course, you may say, what is this interaction? This I am ignoring. Yes, to first order, I can ignore it, but people have done calculations calculating that also, and they don't see, there may be small corrections to this picture, but overall, this gives me fairly good idea about the system. So in the sense, it is not completely wrong. Okay, this is like first order. You can go and add corrections. You can say they add more and more interactions, which takes into the microscopic picture.
Sir, first order corrections, you mean using perturbation theory?
Of course, yeah.
Okay.
Yeah.
Okay.
Okay. So the image. I hope all the other students are also online, right? How many are there? They have left?
Yes, sir.
I don't see any other 47 are there. Good, because I cannot see the screen, other screen. You people have to talk once in a while. Okay. Yes. So, okay. The image loop looks slightly different. You can see that it is difficult to saturate this fellow, because if you apply the field along one sublattice, the other fellow is anti-parallel. So it takes a lot of energy for the magnetic field to flip this fellow along its direction. So unlike ferromagnets, if you have seen ferromagnet curve, if I show earlier, here in this case, you see, it gets saturated very easily. But in this case, if you see, it becomes very difficult. Okay, so your learning potential should be like an antiferromagnet. Okay, at least in my class. So you need to really apply large field. They don't get saturated very easily. But this is important. You understand, like, there can be an anti-parallel configuration. So now I'll go to the next order. We will come back to this little later if you want. Assume that you have an anti-parallel configuration, but the magnitude is not the same. That means in one direction, one atom, the spin is more magnitude of the spin than the other one. Then that gives rise to ferrimagnetism. Why it is more and less? It can be because of different valency state. It can be different because of different atoms sitting at the lattice sides. So there can be many reasons. But it is possible that you can have an anti-parallel configuration, but with unequal magnitude of the spins. What is the advantage? Advantage, immediately you will see that there is a net magnetization along one direction. Like so, your spontaneous magnetization is back again. But it is not ferromagnet. So there is a difference between ferromagnet and ferrimagnet. Ferrimagnet will have a net spontaneous magnetization, but anti-parallel configuration. So examples I have given here, it can be like, iron oxide, cobalt ferrite, all this. Actually, this ferri is because ferrites, lot of ferrites belong to this class of materials. So they exhibit this kind of a antiferromagnetism. So this again, in comparison to ferrimagnets, is slightly the magnetic hysteresis loop looks like more like a rectangular. It's not really rectangular, but this is a kind of a behavior. Okay. Questions? This again, it is a typo here. This is not chi. I will have to correct it before uploading. This is M, magnetization versus temperature. Here again, I will define a TC, beyond which this coupling between the spins is completely lost and it becomes random. So it becomes a paramagnet. Below that, you have this ferrimagnetic order. So I can call this as a TC. In fact, these systems can behave very funnily. We will not get into that now.
Sir, the spontaneous magnetization which you talked about, in case of usually the ferromagnets, so is that spontaneous magnetization is for a particular domain or for the entire system total?
No. Spontaneous magnetization is for a domain. Correct.
Okay. Yeah, so this domain thing exists only in case of ferromagnets, right?
No. Domains do exist in antiferromagnets and also in ferromagnets.
Okay. Yeah. Okay. So in those cases they cancel out. For example, in antiferromagnet case it cancels out.
It cancels out.
And in ferrimagnetism there is a net thing happening.
Yeah. So in actually, okay, let me correct. In the antiferromagnets, if you look at it, if I plot, I did not plot. I have to. I need another device wherein instantaneously I can actually plot. Okay, I will share it in the today evening. See, these two sublattice magnetizations will have a spontaneous magnetization exactly mirror images of each other. Okay, so within the domain there is a magnetization. Within the domain there is a magnetization, but net magnetization is 0. Are you getting my point? In the antiferromagnet.
Yes, sir. Yes, sir. I understood.
So that is clear. I'll plot that and then add it here. So yeah, one has to see. But whereas in the other case, what happens is one will be larger than the other, so there is a net magnetization. Okay.
Sir, why I asked this question is when you were explaining the spontaneous magnetization M versus H curve. So you said that we have to truncate it and then find out from the graph.
That is what, because we are measuring from the internet complete sample. We are no way of measuring. Of course, there are microscopic tools. I will introduce that later. But we are looking at the general measurement is a bulk measurement. That means the entire sample. Okay. So that is why we have to have a method to go to H is equal to 0, because we apply a field. You understand?
Yes,
truncate means we are not really, taking this one and bifurcating the sample. We are measuring the entire sample and we are trying to see what happens to the magnetization when H is equal to 0. So that will give you the domain magnetization actually. Okay.
So when we find out that from the graph, when we truncate it, that is the spontaneous magnetization for a particular domain in the entire atom.
In the entire material, in the entire solid.
Material, sorry, in the entire material.
Entire solid, yeah.
Okay.
Yeah.
Okay.
So, okay. Ferromagnets, if you see, I gave you some elemental examples like, iron, cobalt, nickel, gadolinium, and dysprosium. But lot of alloys and compounds also exhibit ferromagnetism. Okay. And the list is very exhaustive, lot of materials. In fact, many materials. But if it so happens that many of these ferromagnets have metallic character, that means they are like metals. So when you have metallic character, when you apply fields like magnetic fields or electric fields, or you apply large fields, I mean frequency fields with a larger frequency, then there's something called eddy currents. I do not know whether.
Yes, sir.
You are studying electromagnetism. So
yes, sir.
That will limit the use of these materials in high frequency applications for magnetic applications. So why I'm bringing this point is in ferrimagnets, they also have a spontaneous magnetization, but you can see that most of them are oxides. Okay, like Fe3O4, COFE2O4. So these fellows, they are mostly insulators. So these eddy currents, because of the passage of these conduction electrons responding to the oscillating electric or magnetic fields, will not create problem. So these materials are really useful in high frequency applications. So if you go to your mobile phones or many applications, ferrimagnets are used. So wherever you have high frequency applications, that's why they have more characteristics of ferromagnets, but because the materials are not metals, they can be used for ferrimagnetic applications. So in that sense, these are commercially, technologically very useful materials. Okay. And antiferromagnets, because they do not have net magnetization, they are not much useful per se. That means independently, if you want to use antiferromagnet. Okay, I didn't give you example for antiferromagnets. Antiferromagnets are like, cobalt oxide, nickel oxide, iron oxide, FeO, NiO, COO. So most of these materials, they are antiferromagnets. But in these cases, there what happens is only one valency state which is responsible for magnetism. And so the sign of the magnitude of spin at different sides is equal and opposite. So because of that, there is no net magnetization. But in this case, for example, if you see cobalt and iron, so these two fellows will have different magnetic movements. So there is one sublattice will have a larger magnetization and another atom that will be less in magnitude. So it will give rise to a net magnetization. So these materials at this point, you should only know that these materials have a lot of applications in industry. Okay, and also cheap to produce. In laboratories, you can make very easily. So the question now getting exposed to three different orders. So if you remember, ferromagnets, I mean, in the collective picture, I'm not talking about diamagnets and paramagnets, but if you look at ferromagnets, antiferromagnets, and ferrimagnets, so given a material, how do I distinguish between different types of order? So that is the important question. Like in an experiment in laboratory, I want to know, how do I distinguish what is the order in this present in this material? So that is what I'm going to discuss. Is that okay? Yeah.
Yes, sir.
So what I want to do is, actually I will go to the next slide, that is better than this one. Here I can do a measurement, susceptibility as a function of temperature. Maybe I'll show here. Okay, susceptibility as a function of temperature. You see that the susceptibility as a function of temperature, as I showed you in the antiferromagnet cases, you see that they show this kind of a behavior. Okay, you at a nil temperature, they will have a peak in the magnetization, where like both these sublattices will contribute to the maximum magnet susceptibility before thermal energy takes over. But then what happens is it decays as a with temperature. So these fellows will behave like again like C by, like for paramagnets it's simply C by T, and for ferromagnets it was C by T minus T and Tc, and here also C by T minus theta. But then how do you differentiate between a ferromagnet and antiferromagnet, or for the example antiferromagnet and ferrimagnet? So that is a critical question that one has to understand. And I just want to warn you here that from a bulk measurements, that means a simple magnetization measurements, is very, very difficult. It's impossible actually to determine. So one has to do more precise local probe measurements, like a neutron diffraction measurement, in order to tell whether antiferromagnetic order is there. So that is very, very, the detailed things we will see. But a simple ferromagnet magnetization measurement, what you do is you can measure 1 over chi, susceptibility of course as a function of temperature, and then do you have any idea how magnetization is measured? You have any idea? Any one of you? How do we measure magnetization actually? Because we are talking so much about magnetization, and this is a laboratory course, so you should know how we measure magnetization.
Sir, from the current.
What current?
Sir, in the in that hysteresis loop graph, we measured the current going in the solenoid. I don't know about this case, but
okay. So you have studied Faraday's laws of induction, right?
Yes, sir. Yes.
Okay. So what do they say? I'm waiting for a response here.
So change in magnetic flux leads to an induced EMF, induced current.
Yes. So we use that principle to measure magnetization. Okay, one way of measuring.
Okay, sir.
So what we do is, actually next class I will take on the measurement techniques of magnetization before I proceed, so that you should know how magnetization and susceptibility is measured. Otherwise you don't get a feel. Okay. So I have to of course prepare for that. I don't have now, but I will do it. But what you do is, like, you have an electromagnet where how magnetic field can be generated to start with. First we should know that. How to generate a magnetic field?
Current moving in a coil.
Yeah. Okay. So you pass a current through a coil and then you can generate a magnetic field. So how do I measure magnetic field? How can I measure whether magnetic field is there or not?
Sir, I don't know how to measure, but we can detect using magnetic needle. I don't know how to measure quantitatively.
Okay. What's your name? You are Shubham or some?
Yes, sir.
Shubham. Wonderful. I would like to know from other people. Do they know any idea how magnetic field you can measure, or what he said is right? You can feel. You can actually say that there is a magnetic field is there or not by putting a compass needle. Okay. Right? Any other method? How do we know that there is a magnetic field? You must have got exposure to different. How many of you have seen magnets actually?
Yes, sir.
You've seen an electromagnet?
Sir, one more idea I have. I'm not sure. So, in presence of a magnetic field, charged particles deflect, right? So,
Yeah.
I'm not sure that whether it is the answer you want. Like charged
No,
particles deflect
no.
perpendicular magnetic field.
Actually, unfortunately,
So
what happens is we have most of the, our learning is mostly theoretical, right? Unfortunately. So I want you to think in terms of how do I measure? Suppose I go to a lab, what are all the things that you need and how I can measure or
Sir,
it's not a number quantitatively or qualitatively. How do I know that there is a magnetic field? Okay, so two questions I am asking
through
now.
magnetometer, sir.
What is a magnetometer? What does it do?
Sir, device. It is an electronic
Nah, you
device.
have to be more specific than that.
Sir, I don't know much about it.
Okay. So
So by force on a
can we
current
take
carrying
some assignment?
conductor.
Can we take? Sorry, someone is answering. Please go ahead.
someone else is answering.
Yeah, please.
So by measuring the force on a current carrying wire.
Force on a current carrying wire. How to do that? What I'm suggesting is you come to lab. I will give you whatever you want, and you have to set up an experiment and tell me. So can you think in those lines? You have to tell me what are all the components that you need, and what you are going to do, and how you are going to measure. Because see, in the first class I told you, right? Physics is an experimental course, so you should know how to measure. So because we are discussing so many for hours together on magnetization, magnetic field, but we should get a feel what is magnetization, how is it measured, what is magnetic field to start with. We have studied so many courses on electromagnetism, electro-EM theory and all that, but we should know how to measure magnetic field. Anyone has any idea about its magnetic field? What is the strength of its magnetic field?
Sir, how about like we take a solenoid and run a given amount of current through it,
okay,
and change or increase or decrease the current and bring it close to the magnetic field we are supposed to measure, and try to and put a compass in between. So initially you're going to see like what is the initial direction of the compass in absence of any material, like the original Earth's direction.
Okay.
And when you bring the material of whose magnetic field we are supposed to measure, compass will deflect. So now what we're going to do is and bring our solenoid and increase the current or decrease it so as to cancel out the effect of the magnetic material. And from and since it's a solenoid, and we also know that at what distance what magnetic field it produces from the current.
That you can compute, right? Because it's a solenoid, you can compute, you can calculate and tell that depending on the number of coils and other dimensions, you should be able to tell what is the magnetic field expected, right? Because if you know how much current is passing through that, isn't it?
Yes.
Right?
Yes, sir.
Then I can look at a deflection of a compass or something. Then I can say proportionately, okay, this is expected and this much deflection is there. Then I reduce the current or increase the current, and then proportionately I see what is the deflection. So by taking a lot of data, I will be able to compare that what is the field, right? I will be able to calibrate it, isn't it?
Yes, sir.
Okay, so that is one method. That's good, very good. Any other method? Any other idea?
Like place to current
Hall effect.
Hall effect, yes, actually that is wonderful, which we will do in this course. Okay, but what is Hall effect? What does it do? Any idea?
Sir, in a current, when its current is passing through a conductor, and external magnetic field is put perpendicular to it, it deflects the electrons in such a way that a voltage is created perpendicular to where the current is flowing. So if you measure the voltage, we can figure out the perpendicular component of the magnetic field passing through it. Yeah, so that is a Hall voltage, right? So Hall voltage, if you know beforehand, wonderful actually. I think that gives me an introduction to Hall effect experiment. So if you know beforehand how much current you are passing through the conductor and how much magnetic field you have applied perpendicular to the direction in which current is flowing, then Hall voltage is developed in a direction perpendicular to both the current and magnetic field, isn't it? And I do this
a number of times. That means I go on changing my magnetic field strength and go on measuring the voltage. And you see that there will be a linear relation between these two. Okay, the Hall voltage that you measured and the field that is applied for a given current. And in fact, from that slope, you can calculate carrier concentration and things like that, which we'll do later. But the point is, once you establish this, then it becomes like a sensor. Then what I can do is I can take this material and pass the same amount of current in an unknown magnetic field. And if I know how much voltage is being generated, Hall voltage, then I know what is the magnetic field, isn't it? Yes or no?
Yes, sir.
Yes, sir. That's by comparison.
Once I calibrate it, then I can use this as a magnetic sensor. I know that this much field will produce this much voltage. So if I know how much voltage is being produced in an unknown field, I can measure what is the field strength.
Yes, sir.
So that is exactly a Hall sensor. Actually, principle of all sensors is like that, like a temperature sensor. Any idea how a temperature sensor works? What are all the, can you give an example for a temperature sensor? You must have used in different experiments. Give examples, principle of how can I measure temperature? What is the principle? There are many, not one. I can give you half a dozen, but at least you can give me some.
So we're using a thermocouple, sir.
Thermocouple, how does it work?
So the resistivity vary with temperature, and then I can understand.
Resistivity varies. Thermocouple resistivity varies.
The mechanical properties
do not vary, but the resistance.
Okay. Someone was asking me to take only 1 hour. So can I take few more minutes, or I have to stop? Hello.
Sir, you take, sir.
Huh? Okay. So now what I'm asking is, if I have to stop, I don't mind, but I would like you to give an assignment because 1 week time you have. You tell me how temperatures can be measured. What are all the different methods? So please send me this information through email. Okay. What is the principle and what are the different techniques used to measure temperature, both low temperature and high temperature? That basically I want you to get an idea about sensors. How do we choose a sensor? What is the requirement of a sensor? And how does the temperature, and if you know pressure sensor also, okay. So different physical quantities when we are measuring, okay, whether it is magnetic field, whether it is temperature, whether it is luminance or light, whatever quantities that we measure in day-to-day life, what are the sensors that are used? Because now, the everyday life, without our knowledge, we use a number of sensors. So we should know what are the physical principles behind these sensors and how does one choose a sensor. This is very, very relevant in this course because Hall effect experiment, we are doing it not only to learn the physics of it, but it is also a good sensor, magnetic field sensor. It's a Hall sensor. So in that sense, it is important to know what characteristics are required for anyone to choose a particular sensor for a given application. So that general characteristics of sensor, please think about it and then write down whatever you can and send me. And also for temperature sensors, give me examples of different physical principles and what are all the different ways in which you can design or you have idea about sensors. And regarding magnetic field measurement, again, please think about it and then let me know what are all the different ways you can actually measure magnetic field strength. Okay, so those are a couple of 2-3 different assignments I would like to give. Please respond to me by next week. Okay, so with that, I think actually I will stop it here and I will introduce you to the most important concept called magnetic anisotropy next week, which will help us to understand why we have domains. Okay, so this concept I will introduce next week. And also, because I do not want to discuss now how to differentiate, because we should first learn how to measure magnetization. Only then it makes sense to earn susceptibility. So I will also introduce to those 2 experimental techniques. How do we measure magnetization? How do we measure susceptibility? Then from that measured data, how do we distinguish between a ferromagnet, paramagnetic material and antiferromagnetic material? I'll show you this next week. Okay, so with this, and then we'll go to the domains picture. We'll try to understand why domains are there, what decides domains, and so those things we will discuss. Okay, so with that, I think I'll stop it now, and then take questions on either today's discussion or on the previous class. Okay, so I will stop recording now and then